Right, so machine code instructions. I've got an arrow at the top of the screen there. Get some money. Right, in general, all machine code instructions have two components. So they are a pattern of bits, and we split that pattern up into these two base elements. But actually there's three, but we'll get onto that. Right, so we've got the opcode component, and we've got the operand. So the opcode is the instruction. So that's operation code is what it stands for. So that is the actual instruction. So that's operation code of the instruction. And it is just a binary number. When they design the CPUs, the codes they use, they spend a great deal of time because they want it to be logical and efficient to process, and also for the programmer who's working in machine code to be able to like work out and identify it as a class of instructions. So you get groups of instructions that start with the same number of bits and the same bit set. Okay? Right, so the operation code. The operand is the data for the instruction to use. So, for instance, let's look at the Z80 instruction set. Oh, that's the old manual. Which is a humongous PDF. Right, so if we look at an actual CPU manual, this is the list. Now you should remember a bit of this. What do we call these named things that represent the instructions? Oh, what a shame the microphone's not picking that up. That was brilliant. Mnemonics. Yeah, it's one of those words that, like, I suffer with most people's names, is that when you look at it, it doesn't make any sense. So you don't know how to pronounce names. It's why, but everybody's name's like that for me. Right, so these are assembly language mnemonics. Okay? But the actual instruction format, so this is what you get when you're designing computers and you're using a particular CPU, and there are crazy groups, because I'm part of them, crazy groups of people who are building Z80 computers. Even though this chip came out in the 70s, they're still building Z80 computers and 689 computers, and then running their own operating systems on them and all sorts of weird things. There's crazy people out there who know far too much. It's good stuff. So there's a little block diagram there, and you can see that's the registers, and on the Z80 it's got quite a few registers. And you can see this is the chip diagram for the legs on the CPU. So you can see the address bus, and we talk about the width of an address bus. How many bits the address bus? This is a 16-bit address bus. So that means we've got 16 bits to uniquely identify every byte. So what value that ends up on here, remember this is connected to the memory address register, the value that ends up here is the memory location selected, if we're talking simplistically. How many memory locations can a Z80 CPU therefore access? If it's got 16 bits. I'll put you out of my misery. 65536. 64K. Okay. It's a little bit more complicated than that. You can address more memory. The just came out February. It took about 3 years to get manufactured. But a group of crazy people have recreated the Sinclair ZX Spectrum but added all the cool stuff that should have been in the next version of the Spectrum. That was a 1983 computer, but that can address 2 megabytes of RAM. Still uses at 80. So actually what you do is this thing called bank switching that allows you to access far more memory, but you can still only access 64K at a time. It makes your programs really complicated. It's awesomely good though, because it makes them so complicated. You can also see the data bus on this diagram. It's got 8 bits, so you can only transfer 1 byte at a time. So if you're working with a 16-bit value, that's 2 fetches from memory. The CPUs that we use now are 64-bit, so they can grab 8 bytes at a time. Okay, and you can see the other inputs there. You've got the clock. Notice it's got a line above. What does that mean? Yeah, that's how we represent not in maths notation. And you can see quite a lot of those input signals and output signals are knotted. You could probably guess what some of them are. What do you think reset is?
Reset.
Yeah, it tells the CPU to reset. What do you think happens when the CPU resets? No, but what reset? Yeah, reset. No, everything. Everything in the world resets. We go back to day 0. No.
PC goes back to 0.
Yeah, PC at least is going to go back to 0. Might also reset the registers as well. Set everything. But really, you only need the PC to go back to 0 and say like, oh, start again.
Or maybe the accumulator as well. Because if it had like...
No, because the first instructions won't be like saying what's in the accumulator. Because the first instructions were the boot instructions.
Yeah.
That'll be in ROM somewhere. So yeah, no, you wouldn't. Generally, when you're writing firmware for a computer, when you're accessing it raw, what you've got to do, the first job you do is clear all the memory locations. So you actually write zeros to everywhere, just to make sure that there's no residual anything. You know, like when you're told to reset a router and they say leave it powered off for 15 seconds or whatever, and you go, oh, that's a load of coppers. It's just to make sure there's no residual values anywhere. Yeah. So there's clock, plus 5 volts, because that's what it runs on, 5 volt logic, TTL level logic. And then there's a load of other things like halt, wait, and then you've got NMI, which is the non-maskable interrupt. So that's the interrupt that the CPU can't stop. Okay, that's obviously important because you might need to tell the CPU to get off the address bus or the data bus because someone else wants to use it, a different peripheral and things like that. Okay, so that's the sort of, this is the information. Look, you even get the timing information for how long a machine cycle is, and we call them T-states in Z80. And there is the stuff, so the timing windows for everything. This is what you have to work with when you're like setting things up. So let's go to, and you see there's tons of this. So if you know what you're doing, you can. This is all the information you need in order to create a computer system using that chip. And there you go. There is the block diagram that Zilog used to represent the Z80, showing all the external elements. You see how they've drawn the data bus with like a thick banded arrow. Okay. They'll even show you, well, you should know what some of these things are. These are flip-flops. Look, D, C, Q and not Q. That's your D-type flip-flop, isn't it? So that D, now I don't know whether it ever says it anywhere in the spec, but it is what we call a buffer, a D-type flip-flop. So this is used for making a wait state, a one-cycle wait state, because it holds up the data. It's quite clever stuff. Right, okay, so let's get to an instruction.
No,
What?
the way Oli pronounced it.
I'll find the instruction format somewhere in a minute. Right, so you can see here that what we've got, this load instruction, has got 01 at the front of it. So that is the opcode. And then we've got two 3-bit sets. So they tried to squeeze it all into 8 bits because that was the size of the data bus. You don't want to be doing more fetching than you need to. And then it basically, these 3 bits duplicated are used to say where we're loading from and to. So this has got multiple registers. So these are, some of them are just accumulators, others have got compound functions, but you've basically got this pattern of bits. So if I follow 01 with 111, that is where we're going to put something in the accumulator. For the second 3 bits, we're saying where it comes from. So if I put 101 for the final 3 bits, that will say take something from the L register, put it in the A register. Okay, so the operand basically may be the data, or it may be how to access the data. So in this is what we call register direct mode. So we're saying the location of the data is in a register. Those are the sort of quickest instructions you can get, because you don't need to go back out to RAM, because you're staying on CPU. And this takes 4 T states, which is the quickest instruction. They're calling that one machine cycle. So one fetch execute. Okay? So this is the sort of, as an assembly language programmer, this is what you look at, and this is what you pore over when you're trying to like work out how long something takes. So this one's a little bit different. So this takes 2 bytes, this instruction. So it's got the same format. Okay, we've got a code, then we've got a register location, then you get these 3 bits. Now these 3 bits indicate that the data is coming from a memory location. So we're reading from a memory location and putting it in a register. And you can see it takes longer. Okay. So that's what we're dealing with when we're doing this for real. So for us, the operand is the data for the instruction, but it actually consists of 2 parts. So the data part, the operand, is split into what we call the effective address, which says how to interpret the operand. So in that case, certain instructions are hardwired. And there are loads of different addressing modes, and one of the things that people get drawn to certain CPUs when they're building computer systems is the flexibility that the instruction set gives you. And this is the actual, the data set. Okay, so the operand consists of 2 things, an effective address and a data set. Now, as far as the exam board are concerned, the operand is the data. And it just magically, the addressing mode specified. But it isn't, there are some bits dedicated. So if you might use 3 or 4 bits, or you might encode it with the instruction code. And say like, oh, this instruction code uses this addressing format. And it's up to the control unit, once it's decoded, to work out how to interpret that. Now the ones that we've got to learn, again this is generic, but we've got to learn, and I'm going to do this by writing some pseudo assembly language instructions. We have got to know 4 addressing modes. So I'm going to use LDA to say load something to the accumulator, and I'm going to, the symbols I use are my symbols. The exam board will put weird things in because they'll use Little Man Computer and it hasn't got any addressing modes apart from 1. But these are the ones that I will use. So this one is called immediate addressing. So this is where the data in the operand is the data we want. No more fetching required. We've just brought everything from memory, it's there. So that's immediate addressing. So the operand is the data. So we fetched it along with the instruction. There's obviously restrictions on that. You can't have a 2004, I'm turning to Pretty Patel here. You remember when she did that COVID thing and she had to read that number out and it was like, you are kidding me. When she went, it's 700-y, 1000-y, 26 million-y, or something like that. And it was
Got
like,
it wrong, didn't she?
it was a complete kibosh. It's like a year one student should have been able to say the number. It was funny. I'll just find the clip. It was funny. Yeah, so there is a restriction. So if for instance, we have using 5 bits to represent the opcode, that only gives us 3 more bits. So what would be the biggest number in 3 bits that you could represent? The largest number in 3 bits?
3 bits.
7.
No, because this would be 2's complement.
Oh.
3. Or minus 4. Okay, so there are restrictions, but you get a speed advantage. So you can actually think, it changes how you design algorithms. So the operand is the data. So load whatever's there. So the 7, for instance. The one that Little Man Computer's got, and we will do more Little Man Computer, we tend to write like this, where, and this is called direct addressing.
Wait, so which ones are your symbols then?
That is
So
my
that's
symbol.
not what the example.
That just means no, because they don't use any specific thing.
They just tell us which one they're using.
No, they did a really weird question once, and they said, work out what addressing mode it is by telling you what the date was. And it was like, what? Which is a fair question, but not when you've only given 1 mark for it, and you shouldn't spend more than 1 minute on it. I remember when I saw that question, I was like, oh my God, my students are going to go, oh God, what was all that shite? There you go. Right, direct addressing. So this is where the operand is the address of the data. So in this case, it would be load the value from memory address 7. Oops. Oh. Operand is address of data. So this one is, I'll do it in a different colour. This is like a constant, because it will be the same. It's embedded with the instruction. So this is a constant. This is a variable. Right, the third one. We might write like this. This is what we call indirect addressing. And this is where the operand is the address. And if you go to that address, you'll find an address of the data. That's why it's called indirect. We often call this vectored addressing because it's used for interrupt vectors. So I'll put that down, vectored addressing. So that is the operand is an address that contains an address. It sounds a bit stupid, and you think, what are you doing that for? How far do you go? Operand is an address that contains an address. What this allows the hardware manufacturer to do is to specify a set location where if it goes there, it expects to find the address of your interrupt service routine to handle the interrupt. So you can change it in software. So when you load your first program up, the operating system will set the mouse driver location. And if you want to replace it with your own driver, you can by overwriting that memory location. But the hardware manufacturer can like dedicate. So like on Z80s and older computers, you had vertical blank, and that was always at the same physical address. On the Z80, I think it's a hex 38. So at hex 38, you put a jump statement or the address of where your code is. That when the vertical blank happens, the end of the screen's been drawn, you say, right, go and run my code. It's going to do all these like control and timing stuff. Quick! And it happens 50 times a second. So that is the address that contains an address. where we can find the data. Obviously, that's going to be slow. There are others, and don't know why they got dropped, because they're important. So the last one is indexed. So you might have something like this, where you have a base value. Oh, hang on. So let me put index first. Indexed addressing. So that's where we have a base. So and then offset.
So is that what the operand is?
So the operand contains information about the base and the offset. So operand contains the base value and the offset. So in this case, what I've done here, I've said there's a register called X. Okay? That's going to keep track of something. Now this is super important, because this allows us to access data structures, arrays, and we can increment the index register, the X, to access different elements, but we can also use it to access records. So if I know I've got a record of data that's 10 bytes long, I can access the 8th byte of that by saying that offset. If I then want to move to the next record, all I need to do is add 10 to the X register, and I'm immediately accessing that same data item. Awesome stuff. So, base and offset information. Right, so I'll leave it there. What we need to look at is that lot in action. Okay, and run and do some fetch executes on specific instructions so you can see, and you can see the implications of the different addressing modes, because that's important, I think, to understand. Okay, thanks everyone. I will see you next week, is it?
Monday.